Okay, so I'm starting on the back. Now, I'm going to write a couple things on the back that go with this that's not much. Is that still okay as far as, like, not switching, but, like, that y'all aren't seeing, like, that as an issue as, like, going out of order and stuff, right? Okay. Because I really am trying to, like, y'all are making good points and good comments. Like, I really am trying to accommodate to things. I want to use what you guys say to make it better. So I really appreciate what you guys are saying. All right, so a random variable is just the value of a variable is decided by a chance process. And I said I can't do anything about my handwriting. I mean, to an extent, yes, I can. I think I've done terrible with my handwriting, like really, really bad. I'm gonna try to do better. If I need to start writing on the other board, if that helps, I might start doing that. All right, so that's just like if I roll a die, I don't know what the value of the die is going to be. It's chance. Like that shouldn't be anything new. Maybe if I asked you to write the definition of that before, you wouldn't think what to write, but that's fine. All right, so this next topic, still on the back. Yeah. Are you raising your hand? This next thing is actually a huge piece of our class, but in terms of our actual class and material, you knowing the difference, you could really get by with this class without technically knowing the difference or realizing that you're doing different things. But I wanted to at least take a second to address them. All right, so if you think of numbers that are continuous, what do you think of numbers are that are continuous? Like, what does it mean to be continuous? What's your first thought?
1, 2, 3, 4.
If something is continuous, what do you think it does?
Keeps going.
Keeps going. So, like, the number 1, is that continuous?
No.
The number pi, is that continuous?
Yeah.
So, very surface level, you totally get what these are without me really going into them. Discrete, so these are both examples of random variables. That's another thing you guys point out. It's like sometimes I don't finish the connections like that. Possible outcomes. Are separate values. And that seems weird as a definition. And that's not like a book definition, but what this means is if I ask you, how many siblings do you have? Your answers are going to be a separate value. It's not like I'm somewhere in between 1 sibling and 2 siblings or something like that. You either have 1 sibling or 2 siblings or 3 or so forth, all the way up to however many there can be. So what this is, I like to call this things that can be counted. I'll just go ahead and write that example of the number of siblings. So, things that are discrete, I need nothing, no tools. I can count. Like the number of students in this room, I can count. Even if it's something as big as number of fish in the sea, theoretically that is actually still discrete. Now, can I really do it? No. But I could literally count each fish. If time could pause and if they're all that, yeah.
So these always be numbers?
Yes, yeah. So, no, it can be. That gets funny. I don't want to answer that question. Continuous are going to be ones that aren't just separate values. So possible values, possible outcomes. So I'm giving very generic definitions here. Like this is not book wording. But I think you'll be able to use this and see the difference really easily. So the other way I talk about this is things that need tools to measure. Number of gallons in a swimming pool. I can't look at this giant pool and be like, oh look, there's 1 gallon. There's 1 gallon. There's 1 gallon. Unless I'm physically like having something that is a gallon and putting it in there, which means I'm using that tool to measure it. Make sense? But surface-wise, it's the way you think about it. This is something like pi that keeps going on, that can keep going on forever. And these are things that don't.
I get the part in the parentheses for continuous, but not the part not like possible outcomes.
So because I have to measure it, it could be something like your weight isn't just something like somebody's weight isn't just something like 120 or 121. It can be 120.475999, whatever. So like it can take any of those values between 120 and 121.
Oh, okay.
So these are actually really big key concepts in statistics and in our class, but you're not going to be addressed to the fact where like it ever backs up and asks you which one do we need to do and which one do we go from here. It's like right now we're going to deal with discrete. Later we're going to deal with continuous. So today all we're dealing with is continuous random variables. All right, so I'm going to work through a whole problem that you don't need to write anywhere because it's something that we've done before, all that stuff. So what does this symbol mean? What mean? What's the difference between these?
I don't know.
What's this one? Now, if you don't remember these, or you're like, I don't remember that at all, maybe I don't remember that, it wouldn't be terrible to write these four down. What is this one? Standard deviation of the what? I can write it afterwards, but this is sample mean, so this is sample standard deviation. So this one, I don't like the way it looks in text. It's halfway between an M and a U. It's mu. The Greek symbol mu means what? Population mean. And if I've even brought that up once or twice, I haven't brought it up much. No, so this one is, this is the mean of just our sample.
Oh, yeah.
This is the mean of just our population. So, again, I don't like this one type. It looks more like a O with a swirly on top. That's lowercase sigma. And if this is sample mean and this is sample standard deviation,
Then it's
population standard deviation. So up to this point, it wasn't my concern that which one you were using because with what we were dealing with, it didn't really matter. Now I'm going to start getting into differentiating between which one we use and when. So today we're going to end up using these two as opposed to the ones we were using. And I'll explain why. Alright, so this you definitely don't need to write down because I'm breaking down a very simple example. So a mom has 5 kids. She asks each of them how many homework assignments they have that day. And their answers were 2, 3, 4, 4, and 5. Is this discrete or continuous? Discrete. What would the graph of this look like? What's going to be on the x-axis?
Those kids,
What about the kids?
the number of like the first ones.
I could do it that way. So let's break it down a different way. Let's do it with like, we don't care which kid had which. So let's think about it backwards. What would go here? Frequency, and this would be number of homework assignments. What can I always do instead of frequency? Percent, proportion, anything like that. So I could do this one as, I could have done this as frequency and just done 1 and 2, which is the same thing as proportion of 1/5 and 2/5. All right, so looking at this, my numbers on the x-axis go from 2 to 5. What's the middle of 2, 3, 4, and 5? Just not looking at any of this. What is the middle of these numbers? What? 3.5. All right, so I'm starting at 3.5 as my middle, but now I'm looking at what's actually up here. So I had one more on this side than on that side. So what did it do to that mean? Pulled it that way. It's like tug of war. I had 2 people on this side, I had 3 people over here, so it pulled it a little bit farther this way. So it's going to be a little bit more than 3.5. Just thinking through it, right? All right, so let's actually think about how we write this down. So I told you today we're going to do it, and you don't have to write this. I told you today we're going to do it with mu. We'll get there. Symbols equations. How do I find mean? How do I find mean? Add up all the values and divide by the number. Alright, so what are my values that I'm adding? 2, 3, 4, 4, 5. Sorry. How many am I dividing by? I'm just breaking down easy math, right? I could break this down even farther and break it down in pieces. So I can say 2 is multiplied by what? Because I can just write it separate, right? I can do 3 times 1/5, 4 times 1/5, 4 times 1/5, 5 times 1/5. I'm just breaking it apart instead of leaving all over the same denominator. Well, what do I know about these 2? So I could really have rewritten that as plus 4 times, right? What is 2 times 1/5? Decimal, make it easy. 0.4, what's this one going to give me? So 0.4 times 2/5 is going to give me and then that one's going to give me 1/5/5. So it gives me, here I've got 1.6 for a total of. And we said originally we thought that the mean was going to be where? A little over 3.5. Is that a little over 3.5? Yeah. So I just did the talking behind of what actually goes on. Now we're going to connect it to probability stuff for today. Right. So now I'm going to move on to standard deviation, thinking through it the same way. So when I made you do standard deviation by hand, this is really thinking back. We took all of our x values and wrote them down. What did I find with those? So I found our mean, found the difference from the mean. So here's my mean. We found their difference from the mean. I could write all those out. I think I have this on the next one. And then I take all the differences and square them. Everybody with me? This is what we did before. So after that point, I add up all those and then do what with it? So I did 2.56 plus 0.36 plus 0.16 plus 0.16 plus 1.96. So we divided by n minus 1 because it was a sample. Because we have to account for error because it is a sample and we don't know what all of them are. If it's by population, you just do it divided by n. So this will be divided by 5. Everybody with me? Process here. So I can break this down the exact same way I did here. So now I can say, technically, I would say that this is 2.56 times what? 1/5. Plus 0.36 times 1/5. Plus 0.16 times what? Plus 1.96 times 1/5. Everybody with me there? And then once I did this, that didn't give me my standard deviation. I had to do what with this answer to get my standard deviation? Take the square root. So what is... Okay, so let's draw this as a probability distribution. I have my x, and I say we, I mean me. What are my possible x's? What's my probability that it was a 2? Probability it's a 3? Probability it's a 4? And so I just took this exact problem, and now I can look at it this way instead, which is what we did here, which is what we're doing here. So to get 2.56, what did I actually do? How did I get the number 2.56? I started with what? My value.
Minus, well, in this case it would be mu, right?
Mm-hmm.
And then square that.
Right? And then what is this?
Probability of x.
And then I'm going to do what with all of these?
Take the square root.
Yes. What am I doing here? So you just broke down the equation for everything that we need for today. That was the process behind it. It's actually the exact same as what we did. Now we're going to write it out the way we do it. So for me, you're back on the front. That top part just says, remember the probability terms long-term behavior, describes long-term behavior. The mean is long-term average. It's a weighted average in which each outcome is weighted by its probability, which is what we just did. So how do you find mu? So this is mu. We do subscripts here, like this is mu of x, because what variable did I call this problem? I just chose to call it x. If I had put a y there, this would be mu of y. If I put an a there, it would be mu of a. But typically, if we just have one, we call it mu of x. So mu of x equals, how did I find the mu of my x's? Right here. So this was my what value? These are my what kind of values? These are my x values, and these are my probability values. And then I do what with all those? Multiply these, and then do what with each one of them? So it is the sum. Now I'm writing it as xi. That just means you do it for all of them. Your xi times your p of xi. If you write that as is that saying the same thing? This is just saying we plug it in for each one of them. Alright, so variance is something that we have not talked about. I'm gonna write this like what you just told me we're doing for standard deviation. So I'm gonna have a symbol here, so leave just a tiny little bit of space. So when we just found standard deviation, the process we've gotten through so far is right here. We took our values minus our mean and squared it, and then multiplied it by that probability. So we took the sum of our x, each x value, minus the mean value, squared it, and multiplied it by its probability. What is the part of standard deviation that I had not done yet that you told me I was going to have to do at the end? Square root it. So here is just a step before we square root it. So if standard deviation symbol is sigma, what is variance symbol? What have I not done yet? I haven't square rooted it yet, so it is still squared. And I don't ever care if you write the subscript x if we're just on one variable. Your calculator has them as subscript x. So when I am looking at a probability distribution table like this, I call mean, this part right here, I call this top times bottom plus. Because I take this top value times the bottom number plus the top number times the bottom number plus. So I always, that's not a good definition of it, but I call it top times bottom plus. I don't care if you write that. So if this is the equation for variance, what's the only difference with the equation for standard deviation? Has a square root. Really, you can just write, but you might want to draw yourself an arrow that's where that one goes. So whatever answer I got here, I take the square root of it for my standard deviation. So I tried to save you room here so that we can actually do all this in the space. In an experiment on the behavior of young children, each subject is placed in an area with 5 toys. The response is the number of toys that are played with. So this is the entire distribution of all of the options we had made into a probability distribution. So did we use a sample or a population? Population, and that's why we're using mu now instead of x bar. See if you guys can come up with this. Is this a valid probability distribution table? Is that valid? What are things I need to check to see if it is valid? There are 2 things. So 0.3, let me do easy things here. So this together gives me 0.4, and 0.7, 0.86, 0.89, 0.89 plus 0.11, so out to 1. So we know that the sum of the p of x equals 1. But there's a second thing that I want to check. And this one is an obvious thing to check. What can a probability never ever be? And it can't be negative, and it also can't be greater than 1. So the sum of them, all of them equal 1, and all values are between 0 and 1. So is it a valid probability distribution? Yes. None of those are negative, none of them are above 1, and I checked to make sure they all added up equal exactly 1. I checked and made sure all of these added up to equal 1. You don't need to write that, but I did show that to you. Alright, so it is a valid probability distribution, which means I can deal with this. So make a bar graph. I want this simple. Draw it out really quick. Because I'm calling it this over here, what's going to be on my x-axis? X. What's going to be on my y-axis? P of x. Yep. What's the highest y value I have to include? 0.3, right? So this ties into something that I told you in chapter 1, but then it said you don't really know why I'm doing this, but it kind of is a pet peeve to me. What do you notice about the graph that I'm making? About the way I'm putting them on here? So now that we can understand it, why do I separate between bars? Because it is a discrete random variable, which means you are either in this category or the next category. It's not like I can measure in between. With a histogram, can I measure in between? Yes. So in a histogram, do they touch? Yes. So now you understand why I, in the past, have made a point about it, but not been able to explain it. So if I told you to guess, what do you think the mean of this graph is going to be about? Yeah, I don't expect anything perfect. Is it going to be 5? No, it's probably going to be around what? 2 or 3 somewhere, right? Somewhere around in there. Now, I've got more values here than I have here. So, like visually, the middle of this graph is 2.5, but then I've got a little bit more pulling up or pulling down this way, but then I've got more pulling this way. So somewhere around 2.5-ish, maybe. So let's start by finding the mean. So when I am writing out my work for mean, so I'm doing the sum of my x's times my p of x's. What is my first x? How much weight does that pull? 0.03. What's my next value? 1. How much weight does it pull? And I don't know if you've ever heard of things called weighted mean. When I'm saying like how much weight does it pull, like that's what the idea behind weighted mean. What's my how much weight does 2 pull? 0.3. How much weight does 3 pull? 4 times 0.17 and 5 times 0.11. If you use my calculators and you need one, they're sorry, I've moved them off the chair, but they're stacked over here on the floor. If you either get yours out or come get one of mine. What do we get as our mean? 2.68. Is that about what we thought it was going to be? Is that way off from what we thought it was going to be? Taking 2 seconds to look and see if that looks like it makes sense on your graph saves you from issues. It is easy to mistype something. If you get something like 4.7 here, you should realize you said something wrong. So in my graph, and you don't need to draw this on your graph. So if this is 2 and this is 3, then 2.5 is about here. So like, I'm saying my line is somewhere about here. What is the farthest one of my values strays from 2.68? What is the farthest one of my possible options strays from 2.68? So how far is 0 from that? 2.68, right? So is my standard deviation going to be above 2.68? No, so the farthest it deviated from is 2.68, then the average is obviously going to be less than that. So we're probably going to guess that our standard deviation is somewhere about what? About 2, maybe a little bit less than 2. So like the average, so I've got a lot of pull here, which is only 0.68 away. Here I've got most of my pull somewhere between here and here, between like 1 and 1.4 something. So probably my pull is going to be a little bit closer to 1 maybe. Maybe at least just a little bit more than 2. We'll see. All right, so now we're going to do, hopefully have enough room right underneath that, go straight into. So when we do this, we have to find variance first. So I'm starting with my variance. What is my symbol for variance? And again, why did I say that we write an X there? In case you have multiple variables, because I put in my probability chart, I called it X over P of X. So I called my variable X, and that's where that's coming from. Y'all are pointing out a good thing that I don't make connections like that, well, often. So I'm trying to go to that too. All right, So my equation is sum of parentheses what?
xi minus ui or ux
And I do what with those?
squared
And then each one of those I
multiplied by that probability.
multiply it by its probability. So I'm going to take my first value, which is what? My first value is 0 minus, I do what with that? And then I multiply it by whatever its weight was. And then so I'm doing this red as my process that's repeating over and over. That mean is never going to change. I'm always going to multiply it to the probability. So now my next value, what's the next possible value I have? 1. What was 1's probability? 0.16. And then go ahead and write out this equation. I'm going to keep writing it on the board this way, but most of you can go ahead from there. And then type all that in once you've written it down. Making sure we're typing it in the right way. Yeah. And let's go to 4 decimals with this. How you what?
Reduce it to that.
Oh,
It's continuous. Wait, it's.
Yeah.
I was like, wait.
Good, right. I'm trying to write bigger. And 1.7176, right? Everybody get that? So I want to make sure people are typing it in the right way. You should be getting 1.7176 at the end of that. this is variance what we wanted? No, we want standard deviation. Which is sigma of x. So how do I find that? Square root of sigma of x squared. And the square root of 1.7176. Still round to 4 decimals gives us what?
1.3106.
1.3106. For both of those equations, both finding mean and finding variance, we repeated a process over and over for each value level, right? So, is there a better way to do this? This is something we talked about, that if you repeat a process over and over, use a table in your calculator. So let's do this together. So what am I going to put in list 1?
0 through 5.
In general, what am I typing in list 2? Probabilities. So I am going to use list 3 to find mean. So I go to list 3, I highlight up here, and what do I actually type in once it's highlighted?
Parentheses, L1 minus 2.68.
For mean first. I'm going all the way back to being able to find this one. So when I'm just doing this, I just do one with them.
L1 times L2.
L1 times L2. So it gives me all of those values. It's going to give me 0, 0.16, 0.6, so forth, all those as my list 3, right? So then what do I want to do with that list to find mean? So what tells me to add them all together? What will add them all together for me? So I want to do the one variable stat of list 3. And the sum of that list is your mean, which is the same thing that we got when we typed it in. So these are multiplying together. I want to take all the multiplying together and add them, which is what that's doing. So that should still give you your 2.68. Now, I'm going to have people who are like, I hate a calculator. I'm going to screw it up. I'm going to do this by hand every time. Totally fine. You're going to get the same answer. I would rather do it in the calculator. So then when I go on to find variance, now in my, I'm going to do it over here. It goes like this. In list 4, highlight it, being clicked up here, and what do I type in list 4? List 1.
Minus 2.6.
I do what with that?
Squared.
And then I multiply it by list 2. So at this point, calculate the one variable stat of list 4, the sum of that list gives you your what? Variance. And then you still have to take the square root of that to get standard deviation. I would rather do it that way than write it all by hand, but that's totally up to you.